So now I'm going to proceed in looking at the parallelism in the structural patterns. Now, when we first did these structural patterns, we really didn't necessarily think that there was any direct relationship between parallelism and the structural patterns. We thought they might be entirely independently. But as we had more experience in implementing structural patterns in parallel, we saw that in fact each structural pattern tended to be implemented using particular parallel algorithm strategies. So let's move on to the parallel algorithm strategy slice of our pattern language. So the parallel algorithm strategies define the high-level strategies used to exploit the concurrency within a computation when it executes on a parallel computer. And they address different ways with the concurrency is naturally expressed within a problem application. Or to put another way, how do we take the high-level software architecture that we have developed and map that onto a parallel computer? So we see our palette here is of 7 parallel algorithm strategies. Again, for beginners, they're happy to have some kind of particular organized way of approaching how to parallelize a problem. And for much more experienced parallel software developers, they're happy to say, oh, consider all 7 of these ways of parallelizing this application. Then in fact, I've considered all the appropriate alternatives. So let's take a look at pipe and filter and ask ourselves, which of these 7 parallel algorithm strategies best fits? Well, the pipeline parallelism pattern seems to be the most appropriate one. We use the pipeline parallelism pattern when we can describe the system as data flowing through a sequence of computational stages. So we define a set of stages with data flow connections between them, and parallelism comes from the fact that we can have multiple stages active at one time. Now, just as every application typically has pipe and filter at the top level, almost every streaming parallel program will have some sort of pipeline parallelism at the top level. But of course, this is only true if the data is continuously or periodically streaming. If not, then we may not be able to pipeline. So how much parallelism do we find from this pipe and filter? Well, basically, we can get at the top level 1 task for each filter. That's about as much parallelism as we can get. And if we need more parallelism to effectively use our computational resources, we have to look deeper inside the individual filters. Okay, what about the parallel algorithm strategy for the iterator pattern? Among our 7 different parallel algorithm strategies, which one is most appropriate? Well, it's kind of a trick question. In fact, the iterator pattern is the only inherently serial structural pattern in our list of 10 structural patterns. So where's the parallelism likely to be? If we're looking for parallelism in something that's described as an iterator pattern, we've got to look inside the blocks inside the iterator loop. And in fact, we may often find that there are opportunities for data parallelism or pipeline parallelism. Data parallelism if the blocks are entirely independent, and pipeline parallelism if intermediate results from one can be passed to another, or at the very least, we may find some opportunities for task parallelism. Parallel algorithm strategy for MAPREDUCE. What kind of parallel algorithm strategy can we find there? Well, this is the natural place for applying the data parallelism pattern. We can use this when we have independent collections of data which are operated on by a similar, if not identical, sequence of instructions. And we define the collections of data elements can be dated in parallel, and then we define the computation as a sequence of collective operations applied together to each data element. This is very natural for the MAPREDUCE structural pattern. So how much parallelism can we find there? Well, this is the mother lode of parallelism. The potential for parallelism here is as much as the independent number of data sets that we can map onto. Let's look at the agent and repository. What kind of parallelism strategy best maps here? So it's natural to find task parallelism here. We have each of the agents as an independent task, as well as the repository manager of the task. We can also find data parallelism latent in the repository. So how much parallelism does that net us? Well, again, we get about as much task parallelism as there are independent agents. We get task parallelism associated with repository manager. All of these can operate independently. And then, of course, if we have database, say, an integrated circuit is our database, as I've worked in the past, then we may actually have quite a lot of latent data parallelism inside the repository. How about process control? What kind of parallel algorithm strategy can we apply to process control? Well, process control is naturally task parallelism. We can look at the controller, the actuator, the process, and sensors all as independent tasks. Can we think of any other variety here? Well, this may be one of our cases where we have a natural mapping onto discrete event. So the way I think about discrete event is it's simply task parallelism, which we already identified in the process control, together with some sort of time ordering and a timestamp. How much parallelism do we get? Again, we essentially get as much as there are individual tasks, one for the controller, one for the actuator, for the process, and the sensors. Moving on to look at parallelism in the model view controller. What kind of parallelism strategy looks most appropriate here? Well, we see the model is naturally a task, the controller is a task, the view is a task, and we have, how much parallelism is that? Well, that's just one task each, but there may be more parallelism inside. How about layered systems? What kind of parallel argument strategy is most appropriate here? Well, there's a natural kind of organization into task parallelism. How much parallelism do we find? Well, one task for each layer in the layered system. Although layers themselves may again have more opportunities for parallelism. What about event-based systems? Well, event-based systems naturally lend themselves to an approach of task parallelism. Each agent can be an independent task, and the event manager can be a task. Just how much parallelism is that? Well, that can be quite a lot of parallelism if we have a lot of agents in our medium. And again, this is the one case where we get an opportunity for dynamic creation and retirement. How about the puppeteer? What kind of parallelism strategy is most appropriate here? Well, task parallelism seems to be natural. Task for the puppeteer as well as each of the individual puppets. How much parallelism is that? Well, again, it's essentially a one-to-one mapping. We have tasks for each of the individual puppets as well as for the puppeteer. But here we should be looking a little more carefully at each of the individual tasks for greater parallelism. Remember, most likely the fact that we're using the puppeteer is because we have quite monolithic pieces of code and we're using the puppeteer to just kind of synchronize and put them all together. And so there should be more opportunities for parallelism in the individual puppets themselves. Static task graph, what kind of parallelism strategy is most appropriate here, and how much parallelism? Well, as many as there are tasks. So this is a little bit like asking who's buried in Grant's term. In task parallelism, we naturally have one task for each element of the static task graph. So, as we've seen in some of our examples, such as speech recognition, typical application has layers of parallelism. If you look at our speech recognition system here, at the very top level, we have an iterator, which has essentially no parallelism. At the next level, we see a pipe and filter structure, and again, we may be rather disappointed because we found only a modest level of parallelism. And yet, in fact, we found quite a lot of parallelism in this application when we looked at the next level, where we were able to apply MAPREDUCE and find massive data parallelism. Let's review structural patterns and parallelism. So in some sense, structural patterns at this top level of the pattern language are above the concerns of parallelism. They may be used either for serial or parallel implementations. When we attempt to parallelize a software architecture, in fact, our experience is the description of structural patterns may give us only a modest amount of parallelism. There are a few exceptions: MAPREDUCE, agent and repository, static task graphs, and event-based. All these may give us more parallelism. Generally, MAPREDUCE is the only one which will give us a great amount of parallelism. Nevertheless, we found that it's important to use the structural patterns to peel the onion, so to speak. We peel off so that and deconstruct the architecture so it may reveal deeper levels of parallelism in the application. So I'd like to take a step back and overall look at the relationship between structural patterns and parallel algorithm strategy. So this is a tree that you've seen in an earlier lecture. At the top we have an application. We can organize this according to flow of data, we organize this according to tasks, or organize this according to the data itself. And we see each of the 7 parallel algorithm strategies at the leaves of this tree. And what we can see is, for these 10 structural patterns, we see a natural organization of how they map on to these 7 parallel algorithm strategies here below, with the bulk of them being task parallelism, not surprising because it's the most general, pipeline parallelism being used by pipe and filter, discrete event being used by iterator and process control. We didn't find any natural matching to speculation or divide and conquer. MAPREDUCE can often go on to geometric decomposition, or more generally to data parallelism, as can also agent and repository. So again, to review, structural patterns make me feel organized. The modularity provided by structural patterns makes me feel that even the most complex application can be broken down into manageable modules. The result of that is that looking into the underlying structure exposes the parallelism. In summary, again, structural patterns make me feel organized. Understanding your palette of structural patterns is critical to becoming a good software architect. Some structural patterns will help us to identify significant parallelism directly, like MAPREDUCE, agent and repository, arbitrary static task graph. Other structural patterns will just help us reveal opportunities for parallelism. You can read more about this at the website provided here.
Hey everybody, I hope you liked this video. If you haven't seen our other videos on the Intel Software YouTube channel, remember to subscribe and don't forget to leave us a little comment. Tell us what other material you'd like to see and chat with other enthusiasts who watch our shows.